Hello. In this video, we're going to start looking at determining the actual inverse of a function. So the graph of a function f of x is given. We want to construct the line y equals x on the graph, and then carefully plot the graph of f inverse of x by reflecting f of x across the line y equals x. Then determine the equation of the function and its inverse using transformations. Then state the domain and range of each graph in interval notation. Awesome. So on A here, we have this function, and we want to figure out the function, the domain, the range, and we also want to figure out the inverse function and its domain and range. Okay, the first thing we want to do though is we want to go ahead and construct the line y equals x. Y equals x will look like this. Good. Then we want to carefully plot the graph of f of x. That's what we're going to do this here. Plot the graph of f inverse of x. Okay, to do that, notice that there's a point here at positive 2, 0. So this coordinate here is 2, 0. Switch the x and y makes that the coordinate 0, 2. So that point must be on the curve. Go to this coordinate here. That coordinate is 3, 1. Flip those around makes the coordinate 1, 3, which would be right there. Good. And we don't really see any others, but that's enough, really. So we're going to make this curve look like the other, kind of. So there you go. That would actually be the inverse function. This is f inverse of x. Now we want to determine the equation of the function and its inverse using transformations. Now, looking at the original function, the graph right here looks to me like a square root graph. So I know that the original function needs to look like the square root of something. And there needs to be an x in there somewhere. But notice that this is actually the graph of the square root moved right 2 units. Which means underneath this radical, I need to subtract 2 because instead of going plus 2, if it's a horizontal shift, we do the opposite, which makes that a minus 2. Oops. A minus 2. There we go. Good deal. Now, notice that we can actually find the domain here pretty easily by saying that x minus 2 must be greater than or equal to 0. Add 2 to both sides means x has to be greater than or equal to 2. And in interval notation, that makes the domain to be 2 to infinity, including 2, excluding infinity. As for the range, notice we're starting at 0 and we're going up towards the right, so we're going up to infinity. So the range for this function is going to be 0 to infinity. Good. Now here's the thing though. Looking at the inverse function, that is actually a quadratic, or at least half of a quadratic. So a quadratic actually is in the form of x being squared, and notice that the entire function is originally just moved up from normal, up in this case 2 units. So we have to add 2 at the end because it's a vertical shift. But here's the thing, because all x's and y's switch for the original function, that means every x becomes y for the inverse, and every y for the original becomes x for the inverse. That means that the domain of the original must be the range of the inverse, and the range of the original must be the domain of the inverse. Therefore, the domain must be 0 to infinity, and the range must be 2 to infinity. And notice that that's what's happening up here. We're starting at 0 and moving to the right. We couldn't actually use the entire negative infinity to infinity for the domain Because if we did that and we used the horizontal line test, notice that that is not a one-to-one function. As a result, that means that it would not have an inverse. But it did have an inverse. It is the inverse, therefore it has an inverse. So that means that we can't actually use anything to the left, which means we can only use the right half. So here's the interesting thing. If you ever have a function that is not one-to-one, you can create a one-to-one function by limiting your domain. Excellent. That was A. Now let's look at B. So to look at B, let's go ahead and graph y equals x there. There we go. Now we need to find the inverse. Notice that there is a coordinate right here at 2, 0. Flip that around, that makes that 0, 2. So 0, 2 would be right there. We also have a coordinate 1, negative 1. Flip that around, makes that negative 1, 1, which makes it right there. And we also have a coordinate here at, 3, 1. Flip that around, that makes that 1, 3. Good. And notice that we also have coordinates here and here. So this coordinate down here is 0, negative 8, and this coordinate up here is 4, 8. Flipping those around makes that negative 8, 0, which is a coordinate here, and 8, 4, which is a coordinate there. Now notice that there also has to be a point right here because whatever value that is, I don't know the exact value, but because it's on the line y equals x, it has to be on the inverse function as well. And then just connect everything. There you go. Okay. Now we need to figure out what these functions are. Notice that the original function, well, let me label this real quick. This is the inverse function, and I should label this as the original. Okay, so for the original function, this is cubic. Okay, so it's going to be cubic, right? But here's the thing. This is a cubic function moved right. If it normally goes through the origin, notice that it goes through 2, 0. So it's moved right 2 units. So in parentheses, we're going to have to move right 2 in order to do so with a horizontal translation. That means minus 2. Because inside it's always the opposite. And there you go. That is the function for f of x. As for the domain, because it's a polynomial function, the domain is negative infinity to infinity. Also, because it's cubic, it starts at the bottom and ends at the top. Therefore, this is all real numbers as well for the range. And what's great about this is not knowing anything about the inverse function tells me that the domain and range must be negative infinity to infinity, because the domain of the original must be the range of the inverse, and the range of the original must be the domain of the inverse. The question is what about this one? Well, the opposite of cubing is cube rooting, and that's the form that we see here. This is a cube root function. Now, I'm going to put the x on the inside because notice that this is a cube root function moved up 2 units. So I'm going to, at the end, add 2, and that's going to be outside of the radical. Well, let's make it a little bit easier to read here. So cube root of x, and then plus 2 outside the radical. Alrighty. Well, I believe that's it for this particular video. I'm going to go ahead and end it here, and I will see you in the next one. Have fun.